Okay, so here we're gonna start trying to develop our algorithm for matrix multiplication. Now we'll first start with the matrix vector product. Okay, now we've talked about forming linear combinations of the columns of a matrix, right? And if we have a matrix A, where if we define right the columns to be column vectors, right, which we'll call A1, A2, etc., all the way up to AN. All right, and we have some vector x in our Euclidean n space, n. All right, and here we'll say A is m by n. So there are m entries in each one of these vectors. All right, and we define this A times x as the linear combination of the elements in here, let's use proper vector notation here. X1 times the vector in A1 plus X2 times the vector A2, etc., all the way till we get to Xn and the vector AN. Okay. Now notice here that the result, we're adding vectors. These X1 through Xn are scalars, right? And each one of these vectors is m by 1, right? So when we add this here, so the result of this here is some n by 1 column vector. Okay? All right. So here is an example here. Let's say we had a matrix here, and then here, one more row here. And we want to multiply it by the vector 1, 2, 3. Right, so the above statement tells me to multiply 1 times the first column vector, which is 1, negative 2, negative 1, plus 2 times the column vector 3, 1, 0, and then plus 3 times the column vector 4, negative 1, negative 1. Right, and then working this out, we see that gives us 1, negative 2, negative 1, plus 6, 1, 0, plus 12, 6, 2, 0, 12, negative 3, negative 3. Right, and then finally adding these up, we get the column vector 19, sloppy writing here. So 0, negative 3, and negative 4. Okay. All right, so we have defined this matrix vector product, right? And we'll use this as our starting point for just multiplying two matrices, right? But for now, this is what we'll start here, right? And we'll build on that in our next video here, right? But what this kind of leads us to do here is we want to define, right, or introduce a theorem in our textbook here. So if we look at our textbook, we see here we have, excuse me, theorem SLEMM, so systems of linear equations as matrix multiplications. And the theorem states is the set of solutions to the linear system LSAB equals the set of solutions for x in the vector equation ax is equal to b. All right, so really what we're introducing here is a new way to write, instead of using this LS notation with a matrix A and then a column vector B, now I can write it as a vector equation, right? Or here, what this is hinting at is, let's go back here. Right, so then moving forward, all right, so what we have here moving forward is, right, for our system LS linear system, where we have coefficient matrix A and B, we'll be using now the more compact notation here, the vector equation AX equals to B, right? Where here, that vector B, that's the solution vector, which is m by 1. This vector will also be m by 1, right? Excuse me. Excuse me. This vector is n by 1, right? And then our our coefficient matrix A is an m by n matrix. And we saw in the previous example, the product of AX together, this product is an m by 1 matrix. So the dimensions match up, right? Again, we talked about earlier, we showed the equality of matrices and vectors in the previous video, is that they needed to be of the same size. And here we see that this equation, right, does produce two vectors of the same size, right? And our vector x could be the variables themselves, just x1 through xn, or it could be actual solutions to a system of equations. All right, so we'll use this type of notation moving forward. All right, so for example, right, if we have a linear system, like let's say we had x1 plus x2 minus x3 equals to 0, and then negative x1 minus 3x2 plus 5x3 equals to 9, and then 3x1 minus 7x2 plus 5x3 equals to 4, right? The way we can write that now is we can write this as the matrix A, being the columns are the coefficients here for our x1 variable, 1, negative 3, negative 7, negative 1, 5, 5, and then we can have the column vector be x1, x2, x3, and then equals to the vector 0, 9, 4. All right, over here, AX equals to B. All right. Okay, so now it comes down to solving this vector equation, right? And then when we get into more properties of matrices, it'll come down. We'll focus on that matrix A and what we can determine about A, what that tells us about solving an equation like this.